Hi, my name is Nitinder Mohan and I'm a postdoc researcher at Technical University of Munich, Germany. Today I'm going to be talking about our work, Pruning Edge Research with Latency Shears. The work is done in collaboration with researchers from Uppsala University, Sweden, University of Twente, Netherlands, and University of Helsinki, Finland. In this presentation, I will discuss the overview and importance of edge computing research and will try to showcase several assumptions that the research community falsely makes about the field. Before we start to discuss edge computing, we need to understand where the field arose from. The figure shows a typical configuration of a cloud computing environment. The cloud can be viewed as a centralized large-scale deployment of data centers to which different users and applications can connect to from different parts of the geographical region. Cloud was a huge success since its inception, as the type and the volume of the application's resources could be elastically adjusted to meet the demand on the fly. Since the data center farms are carefully managed and controlled, the cloud boasts of high level of reliability that allows applications to scale their reach globally. Edge computing came to the scene in circa 2009 with Cloudlet's paper from Professor Satyanarayan. The idea behind edge computing was simple: decentralize the cloud computing and put compute services closer to the user. The primary motivation surrounding the research was the large latency that the users had to endure to connect to a cloud data center. The idea started with the deploying of managed mini data centers in infrastructure which are closer to the user, but soon spread like wildfire with many proposals pushing computations to smartphones, routers, and even IoT actuators. The need to push the envelope further and further was justified by the fact that the compute requirements were no longer limited to user-facing applications, but were being driven by next-generation applications, the likes of AR, VR, autonomous vehicles, etc. And unlike users, these applications impose strict latency and bandwidth demands that the current cloud environment does not satisfy. So before we proceed further, let's first try to understand what are the next-generation applications that are driving the hype around edge computing and what requirements do they impose on the underlying network. We analyze the existing publications on the subject and categorize the next generation applications based on their latency bandwidth requirements. The y-axis shows the required latency that can range from a few milliseconds to an hour, and the x-axis shows the amount of data that an application can generate ranging from a couple of megabytes to several terabytes. We found that the majority of applications are human-centric in nature and are therefore governed by the human vestibular thresholds. The most stringent threshold is known as the motion to photon, which is the delay between the user input and its effect to be reflected on a display screen. MTP latencies are estimated to be around 10 to 20 milliseconds and can result in motion sickness and dizziness if not adhered to. Maintaining latency below MTP is critical for immersive applications such as augmented reality, virtual reality, etc. The second latency threshold is perceivable latency, which exceeds when the delay between the user input and visual feedback becomes large enough to be detected by human eye. PL threshold is estimated to be around 80 to 100 milliseconds and is critical for interactive applications such as cloud gaming. The final threshold is the human reaction time. It is the delay between the presentation of a stimulus and the associated motor response by human. HRT threshold is often estimated to be around 250 milliseconds and is required for applications that have active human engagement, like remote surgery. It now becomes easy for us to place all the applications on this latency bandwidth graph. The form and the orientation of the application represents its strictness towards the latency and the bandwidth constraints. The application's color denotes its expected market share by 2025 in US dollars. Based on the similarities, the applications can be broadly divided into 4 quadrants. Quadrant 1 on the bottom left encompasses applications that require low latency for operation but generate quite low data. Quadrant 2 holds applications that generate both large volumes of data and impose strict latency constraints. Most of the hyped applications like autonomous vehicles fall in this quadrant. The quadrant 3 is composed of applications that generate large volumes of data but have relaxed timing constraints, while quadrant 4 on top left is composed of applications that neither generate large data and have very low latency requirements for operation. Now that we have quantized the requirements of next generation applications, we can ask ourselves the question, can the cloud really not support the requirements of these applications? Our curiosity stemmed from the fact that the state of cloud computing infrastructure has changed significantly over the past 10 years, with many more cloud providers entering the markets and big providers like Microsoft, Amazon, and Google expanding their existing infrastructure to more geographical regions. On the other hand, almost a decade has passed since the edge computing was introduced in the research community, and yet we do not see any large-scale deployments to support its claim. To this end, we reevaluate the latency-centric claims of edge computing with extensive global wide area measurements to data centers of major cloud providers. We targeted 101 cloud regions from 7 major cloud providers shown in the figure, which have significant global coverage. We explicitly selected to target regions which offer compute capabilities and install a virtual machine as an endpoint. Our selection provides us a good mix of providers that have deployed their own low latency network backbone versus those who use public internet infrastructure for interconnecting their data centers. For our vantage points, we rely on RIPE Atlas, which is considered to be the de facto platform in the internet measurements research community. The Atlas probes are installed in varying network conditions and allow us to analyze user reachability to the cloud globally. We use 3200 plus probes distributed in 166 countries, which we get after filtering out all the probes that are clearly installed in privileged locations. For example, in data centers, cloud networks, ISP infrastructure, etc. For our experiments, we measure end-to-end latencies between the probes and the data centers by ICMP pings that repeats every 2 hours. All measurements have been ongoing since September 2019, and in this work, we draw results from 9 months of data collection. Our dataset spanning several gigabytes is available for public use. Please refer to the paper or the end of the talk for the link. So the first question that we answer with the measurements is the spread of the cloud across the globe in terms of latency. The plot shows the minimum ping latency observed by the best performing probe for every country to any cloud data center. The red diamonds denote the locations of the cloud regions that we target in our measurements. Firstly, we can observe that a total of 32 countries can access the cloud within 10 milliseconds, and 21 countries can access it within 10 to 20 milliseconds. Together, these countries form about 70% of the world population, which showcase the effects of immense growth of cloud infrastructure, unlike assumed otherwise in the edge research community. The reasons for the low latency becomes clearer when you correlate them with the deployment trends of cloud data centers. We find that 80% of the probes in Europe and North America, which have the densest cloud coverage, which also equates to 50% of the total probes in our measurements, can access the cloud data center within 20 milliseconds. The latencies are a bit longer in continents which have low availability of cloud and effective network deployments. For example, we find that almost 75% of the probes in Africa and Latin America can access the cloud within 100 milliseconds, and in total, 80% of the probes could reach the cloud within the perceivable latency bounds. We also observed that almost every probe except a few in Africa could reach the cloud within the human reaction time threshold. While in this presentation, we only cover a subset of the results, I encourage you to refer to a paper for more detailed analysis. But all this looks fine and dandy, and it might lead us to another question. Where is the latency? The CDF above shows the latency distributions of all measurements from all probes grouped by continents. We also mark the latency thresholds of the next generation applications for correlation. As we can observe, things start to get really interesting here. Despite the extensive reach of the cloud, the results indicate that only a fraction of probes in Europe and North America can reach the cloud within 10 milliseconds, as required by the motion to photon-based applications. For continents with dense cloud deployments like Europe, North America, and Oceania, it is largely possible to reach the cloud within 100 milliseconds and support applications like cloud gaming. For Latin America, Asia, and Africa, cloud reachability is quite poor, and only a fraction of probes can satisfy the perceivable latency thresholds. Probes in Asia show much diverse latency due to the scattered and clustered data center deployment favoring a few countries like India, China, Korea, etc. We observe the worst performance in Africa since it is severely underserved in both cloud presence and network infrastructure. Another major cause of long latency to the cloud can be due to the wireless last mile. Many studies in the recent past have shown that the wireless medium in both cellular and Wi-Fi is the primary bottleneck due to the frequent packet drops, handovers, etc. To showcase the effect of the wireless connectivity in our measurements, we filter out probes that the user tagged as using wired connections, for example, Ethernet broadbands, and probes which were tagged using wireless keywords. Further, we filter out probes that were deployed in the similar regions for both sets and plot their latencies to the closer data centers. It is evident from the box plot that the probes tagged with the wireless perform considerably worse than the wired counterparts, often taking 2.5 times longer to access the nearest cloud region. Our result is in line with the other previously measurements on this topic that show that the users can experience approximately 10 to 40 milliseconds added latency when using a wireless last mile. In fact, a recently published study from Nokia Bell Labs showed that the latency gains to connect to an edge server at the closest LTE base station is minimal compared to a cloud data center which is located thousands of kilometers away. New technologies like 5G promise much shorter latencies, but recent investigations show otherwise. Learning from our observations, we can now revisit the next generation application requirement and plot the regions of edge reality. The latency feasibility zone of edge computing is shown in the red. The lower bound of the zone is about 10 milliseconds, which through ours and previous analysis in the area is the average wireless last mile access latency. Even if the edge server is placed at the nearest base station, it would still take approximately 10 milliseconds for the user to reach it, thereby making motion to photon latency almost unachievable. The upper bound is the human reaction time, which, as we observe from our results, is the time within which almost every region around the globe can access the cloud. The region in blue shows the bandwidth feasibility zone of edge computing. Edge is most useful for applications that generate enough data to congest the network. Specifically, the benefits from the edge are greatest close to the user and decreases with increasing distance, and can be further affected by contention at the last mile. Based on the previous studies, we estimate 1 GB per entity data generation to be the lower limit for bandwidth threshold. The overlap of the two feasibility zone gives us the edge computing operating reality. The applications in this zone clearly benefit from the deployment of edge, as they benefit in both latency and bandwidth. Interestingly, many hybrid applications that are used to motivate the need for edge computing do not really fall in this zone, because either the requirements are too strict or they are too relaxed. Moreover, the predicted market share of the applications within the feasibility zone pales in comparison to those for which edge do not really provide much benefit. But does this mean we are heralding the end of edge computing? No. Our aim in this work is to showcase that in light of the recent trends in cloud computing, the reduction in latency argument no longer holds true for edge. However, we want to stress that the latency is only one piece of the puzzle, and there are other considerations that are more convincing drivers for edge computing. For example, the inherent privacy that the edge provides by decoupling processing from centralized management, to bandwidth aggregation gains, to enabling distributed MLAI application, to providing a localized computing context. The benefits of edge are many. We identify several promising research directions in our paper, which you can refer to. With that, I conclude my talk. These are the references used in this presentation, along with a link to our measurements dataset. If you have any questions or comments, you can please contact me on my email address. Thank you.